I want to thank y'all for coming to Reeves County and participating with us. I'm a local boy. We broke out here 6 generations ago with the spring and Boundary on our way to Prescott, Arizona. The family did. We've been stuck here ever since. I was fortunate enough to go to Sul Ross State University, where I was trained by some of the best geologists in the world. They had named faces on the crater of the moon, all kinds of neat stuff, and then I was able to go on from there. And we lost a lot of really famous geologists in West Texas this year. And when I looked around, all of a sudden I'm one of the old ones. And so the maps that I'm about to show you have been put together from some of the most famous geologists that have ever walked in West Texas and North America. And what I want to do is share with you about why Reeves County, West Texas, is so geologically significant. Out here in West Texas, we can look at 1.6 billion years of Earth's history. And when we look at this kind of a thing, most people just think, well, it's just a nice, pretty map, right? When you actually start deciphering it, there's even prettier maps. And the more complicated a map gets, the better they become for us. And so when we look at this, there's a mountain range that comes down right through here that is actually known as the Ouachita Marathon Thrust Fault. That is the bottom of the Appalachian Mountains. And it overprints an existing thrust belt called the Grenville. The Grenville is exposed out here in Van Horn. It's exposed a little bit in Central Texas. That's a 1.6 billion year old mountain range that represents the formation of a supercontinent called Rodinia. And it is the first mega supercontinent in Earth's history. And the suturing of it occurs in my backyard, right here. And most people don't realize that. And then it breaks apart. And when it broke apart, it went into just really fascinating microcontinents and megacontinents. And then it comes back together right here again with the Marathon Salient. It starts in Newfoundland, comes all the way down the East Coast. There's 7 suborogenies with the Appalachians. The last one is right here in West Texas, exposed at Marathon, Texas, and represents the formation of Pangea. So the next supercontinent comes together, and breaks apart again. And this was about 250 million years ago. What it did for us is it created the Permian Basin. And as a result of this thrust belt, the land will uplift, gets shoved upward, and we create a flexural basin behind it. It's a tectonic basin. And if you picture the mountain ranges over here around Lando, tall as the Himalayas, we begin to erode them and we transport them our direction. And as we load this basin, it begins to sink. And the subbasins are just fascinating. How this geology comes together and the structures of it and the history of it is just unbelievable. So when somebody steps out here and they say, well, I don't know why you guys live here, there's nothing to do. Well, there's plenty to do. And so you fast forward a little bit, that breaks apart. Then we have something else fascinating happen. The North American 40 area comes in. The Davis Mountains are the base of the Rockies. We're compressed again from the west. We create a mountain range out here that's volcanic. And it is unbelievable. So now we have structures. We have 3 sets of structures, right? They call these deformation events. We have D1, D2, D3 event. Now we're down to a D4 event. And all of these things are creating faults and fractures and all these complexities. Each step of the way, we're adding more complexity. We fast forward a little more, we begin to expand into the widest mountain range in the world. It goes from Bishop, California to Pecos, Texas. And that's basin range extension in the North American 40 area. Basin range extension starts 20 million years ago, and you see a shear zone. I'm going to go through this a little more in depth here in a minute. And then it begins to do full-blown expansion. So as you drive from here to western North America, you'll see a mountain range, right? Flat area, mountain range, flat area. That's what you're looking at, a series of drop-down things called crawlies, up-thrown mountain ranges called horse. So now we've overprinted it 2 more times with more stresses. So West Texas, when you step out into Boundary, Texas, and y'all are gonna see some amazing science today about the water and water quality and all of this. But it's important to remember that the structures are what's causing it. And between these structures, in Texas, we have this great map. You got the high plains. These are the geologic provinces of Texas. The land of uplift is so significant that it is its own province. And then you got the green here, it's Cretaceous. Now I'm about to show you how this formed and why it's important. So between these tectonic events, you start seeing major global flooding events. So right here at the bottom, you see that Precambrian. That's before life actually existed on the planet for the most part. You see a Cambrian explosion. Well, why do you see an explosion in life? Well, tectonics driven things around, and we start seeing all of the globe's flooding. So these tectonic events of continents building, breaking apart, we begin to start creating oceans on places we might not normally see. There's 6 major transgression or continental flooding events under our feet right here. If we were to drill a hole down to the granite, we're going to encounter all of these rocks in this area. So I'm not going to bore you with the fancy names, but they're kind of neat. And they're exposed at type locations. And as we go forward, each time we see a major mass extinction, which you start seeing the geologic time scale come about, and you tie this stuff together with tectonics along with the flooding events, and it cause it all this great stuff, and then we start traveling Texas, and we start seeing cool things. This is the basement, oldest rock in North America, exposed right here in central Texas. And look at it. All right, geologist, what is it? Right here, you know what this is. I'm taking you to this outcrop. There you go. It's the packed out schist, oldest rocks that you start seeing, and the basement's under our feet. It's exposed out here and also at Van. And so when you get into this stuff, this is what the basal granite looks like. And then it's exposed in central Texas, exposed out here in west Texas. It's under our feet, several thousand feet here, covered with all these detrital zones. But it's important that this is here. And when you think about, I encourage you to think about this. We throw a lot of terms around on these earthquakes and things lately, and what's causing them and why they're being caused. And people will say they have an answer. There's not an easy answer. There's going to be pre-existing faults in zones. There's going to be pathways for water to mobilize, all kinds of complexities that we have to think about. And we use science to try to get there. This is my favorite geologic picture there is, the Great Unconformity. This marks that first flooding event of the globe. So this is the Precambrian, this is the Cambrian. You can see this right outside of Mason, Texas. And you can see it again. We were able to drill a hole and scratch the basement out here anywhere in West Texas. You can see it well logs. It's really, really interesting. Above it is the most famous sand in the world, the hickory sand, which is known for frac sand until we started using some of the sand dunes out here. This is the most spherical sand on the planet. They shipped it all over the place. It's associated with the first major flooding events laid in here. And you can see it exposed in lots of other places, like Hoover Point outside of Kingsland. These are really, really just famous outcrops that are created here. Here's one in Mason, Texas. Now this has the oldest life on the planet. It's actually there. You can see it in West Texas in a couple of places also. But these are stromatolites. They're Cambrian age stromatolites. First life you start seeing is right here in our regional geologic setting. Only other place these things are still alive, by the way, in modern environments in Western Australia. You can see some of this kind of stuff still occurring. Now, the North American Seaway, we have the Appalachian Mountains here, old. These mountains don't exist yet. And this is the Cretaceous Seaway, which is the age of the dinosaurs. And so we're completely underwater. This is responsible for all of the limestones we see making up the Edwards Plateau, laid down during this period of time. Cover all of Texas. If you guys travel Texas, the rock, though, gets confusing. It's the same rock with about 8 different names because geologists are slow and they like to not name things all uniformly. So it took me forever to figure out what these rocks' names actually were. During this time, and what's so significant about where we're standing is there's a major deep ocean system off here to the south. You got a reef front, which is exposed right outside of Geologic, this place called Lost Maples. If you ever get to go there, you can really see these rocks. We live in the lagoonal system, backwater system, and so we see lots of evaporites and things of that nature here in this time. These are what these rocks look like. They have holes all in them. They're carbonates with bugs. This is the beginning of the caverns. And when we start seeing cavern development, this is what starts with the fossils dissolving out of them and fractures and faults. Water begins to move. When water falls from the sky, has a pH of about 5.4, slightly acidic. This rock has a pH of about 8.2, so you're going to have an acid-base reaction. Every water that we see is going to have distinct chemistry. And it tells you its life history, how long it's been in the ground, and what it's come in contact with. Now it leads us to this, which is what we're here for. What is hydrogeology and what's an aquifer? So if you ask my little boy what's an aquifer, he's going to tell me that it's just where you get water in the subsurface. Pretty simple, and he's got it correct. Now when we start looking at them, they get broke down, and I want to break these down so that we have an introduction as we get started and moving forward for the rest of the day, kind of set why these things are important. Each one of these aquifers is a zone of saturation, and there's going to be layers of rock in the subsurface. And so you're going to have zones that are confining layers and zones that are unconfining layers, and we're going to have aquifers that, if you drill into them, free flow, come out under pressure, and we're going to have ones we have to pump. They are all interesting in their own way, and the way we get signatures on them is by research. And I've spent my tour of duty for about 20 years in Western North America obtaining aquifer data. And this is what we do professionally as geologists and engineers. And then we tie it all together and we make these great schematics about how water gets in the subsurface, how it flows, and how it comes out. But it's not this simple. Is my whole point is it's ultra complicated stuff. And then somebody brought up TDS a while ago. What is TDS? Well, it's total dissolved solids. It has to do with how much dissolved ions are actually in a water. And there's breakdowns in what's fresh water, what's brackish water, what's brine water. And this is how much dissolved stuff is in it. If I was in a tub of pure water and you threw a toaster in with me, it will not conduct electricity because there's no dissolved ions in it. But if I got Pecos, Texas water, and you threw that same toaster in with me, you're going to ruin my afternoon. So these things are broke down, and each water is different, and each signature of water changes as you travel the nation. Some of the waters on the East Coast are more acidic as you get toward the west and become more basic. And it has to do with the rock type and the age and the time that these waters spend in the subsurface. And so with each one of these things, these are what we refer to as the major eights. This is where we get the TDS. These are dissolved ions that we actually look at. Each one of them tells us a story about the rock that's coming out of it. If you have a sandstone rock, your TDS typically are going to be lower. If you have a carbonate rock like a limestone, we start crawling up. We got things like the Slato Formation and that kind of rock. We see this like salts. We start climbing way up into these brackish zones. We also start trying to track these things and what drives the water chemistry. And lots of them are going to be just based off evaporation and weathering of rocks. There's chemical and physical weathering, and how do we break down this stuff? As we move through, we have to take all of this into consideration. Earlier we heard something about nitrate, right? Nutrient cycling. Agriculture gets blamed for 90%. I'm just going to get on the soapbox here. 90% of us in ag get blamed for the nitrates. It's not human. It's not ag. It's human. It's failing septic systems and straight pipes. I mean, and we know this by doing other DNA type work on our waters. We can now track where fecal material in water came from, and DNA specific is back to where it originated, be it human or dog or cat. You know, it's crazy the kind of stuff we've been doing in our labs lately. So we can answer lots of questions. When we get into this a little further, we're going to try to figure out, now we got a complex system, we've got a rock, how in the hell do we figure out how a fluid moves in? Now this comes down to somebody, craftsman named Darcy. This is his equation. Now Darcy was just a pretty neat engineer interested in putting sewage in pipes. That's how we got all of this. This is where the entire field of fluid dynamics begins, is with these little simple equations that calculate area and rise over run pretty much, and what a system looks like. And these K values are like how much water can flow through a matrix. So as y'all move through today, I wanted to give you an introduction of what some of this stuff means, because we're going to get a lot of terms thrown around. And let me tell you what, groundwater guys love their terms. That's our downfall. And so anytime you see a term that's thrown up here, ask Dr. Green to define it, because it's going to be we can't communicate properly. So when we get into these aquifers, every one of these things now has a fingerprint, and we get to figure out where they are and where they come from. In Reeves County, there's major aquifers and minor aquifers. These are our majors, Edwards Trinity and the Rustler. Each one has a distinct chemistry associated with them. Both of them pretty high TDS. And then we have minor aquifers, and like the Dockham and so on. And I put this regionally because these are our regional maps. It turns out water does not stop at county lines, and it does not stop at state boundaries, and it does a lot of stuff that causes some people indigestion. And it also does not stop at my ranch boundary going to my neighbor's ranch. And so now when we start seeing these problems develop, and we're trying to pump waters and conserve waters, we have to know what they're coming out of, how long they've been there, where they're moving. We have to quantify them, and now we got legal issues with them, right? All of the above are things that every one of us in the room are concerned with, and we're on the same team trying to solve and work. And I cannot stress that enough. We're all working on this so that our kids have something to go look at. So right here in Reeves County, very, very famous place, actually. And it's recording all of this history. And we need to start going on some more field trips and getting out a little bit more. But as we move forward here today, keep this in mind. The complexities of this are just unbelievable. And the amount of human manpower to map these. This stuff was mapped originally by P.B. King on a mule. He was so old he couldn't walk on foot anymore. I don't know if y'all know who he is. He's one of the most famous geologists ever in North America. He's the guy that created these maps, and 90% of his work's still correct today. So he was that good. We haven't been able to fix it. Can't fix it because it's not broken. But when we're drilling these wells and things, we got a lot to keep in mind. And so I'll take any questions y'all might have out of me on any of that stuff. There's 1.6 billion years in it. All right. Well, I'll be around.